Hi guys, welcome to GCSE Geog Support. What I'm going to attempt to do in the next couple of videos is go through each of the units, as many as I can, all in one video, and talk about the main key terms and the main processes. So I'm going to start with Unit 1, and what I've got here is I've got some boards and I've got my textbook, and I'm just going to run through some of the kind of key processes and stuff like that. So I'm going to crack on because there's quite a lot to do and it might be quite a long video. So we're going to start off with the first unit, which is Hazardous Earth, and the first section of this is global warming, and it goes on to hurricanes. So we're going to start with the first word, which is global circulation. And global circulation is talking about the three cells, basically our three cells. And we have got, if you remember, we've got the heat being the most intense at the equator. That causes the air above the earth to get hot. That causes that hot air to rise. Remember, when air rises, it causes low pressure at the ground. That warm air rises, cools, condenses, forms rain, and we get rainfall. So low pressure means rainfall. Now, remember, when that heat rises, it cools, condenses, turns to cloud. It wants to drop back down, but it can't. So it spreads out, and it spreads out either side of the equator. So it rises up, spreads out either side, and it drops back down again over the tropics. And that causes high pressure. That causes high pressure because the air's sinking. Now, sinking air doesn't cool and condense, so that causes dry conditions. Okay, so at the equator we've got wet conditions, and either side of the equator in that first cell, that Hadley cell, we've got dry conditions. So that's our first circulation cell. So it's doing this either side of the equator. So hot air is rising, cooling, condensing, forming clouds, spreading out, dropping back down. Then that air will warm again because it's the tropics. So it warms again, and it wants to rise, but it can't rise because the air is still dropping on top of it. So it goes back in to that low pressure belt and it rises again. So you've got our circulation model. And that band in the middle at the equator is the ITCZ. Okay, I think that's our next one, is ITCZ. So that leads us quite nicely into that. So the ITCZ is basically the band of rain at the equator. Okay, now I might be getting ahead of myself a little bit here, but that band of rain at the equator kind of moves. It doesn't move because the Earth is spinning around the sun and we're on a slight axis. Sometimes it's facing into, it seems like the Earth's facing into or towards the sun, and sometimes it seems like it's tilted away, but it's just that it's going around the sun like this. So sometimes it's tilted away, sometimes it's tilted before. If you see my head as the sun, then if it's going this way, this is the Earth, imaginary Earth with my two little axes. It's not on a, it's on a slant, and we're tilted away. So that's why we've got winter now in the UK. Then it goes back around again, and it's tilted towards the sun. Now, so that's what happens in the question. You're quite often asked about rainfall in West Africa and why you have rainy seasons in West Africa, and that's basically because West Africa is kind of going into and out of the ITCZ. So that is the ITCZ, the Intertropical Convergence Zone, and it just means a band of rainfall. Okay, so the next one. Let's stay with the global circulation because there's quite a lot to talk about there. So when that global circulation, those cells start, the Hadley cells, it's going around, and some of it, though, when it drops down at the tropics, some of it goes back into the equator and some of it goes outwards. So as it goes outwards, it comes towards us. We don't really consider the southern hemisphere really because it's mostly ocean. So it comes towards us in the UK, and it is warm, so it wants to rise again, so it rises up, and it causes another band of low pressure. So remember what we said, low pressure means hot air is rising, or warm air is rising, cooling, condensing, forming clouds, so we get the second band of rain. Okay, so whenever we've got low pressure at the equator, in the mid latitudes where we are, we've got rainfall. Okay, now that warm air rises, cools, condenses, wants to drop again, spreads out and drops back down. So it goes back into the Hadley cell, that's a feral cell. And then some of it goes up north to the North Pole where it gets cold, it drops back down again. That causes high pressure. So then the polar cell, that's a dry desert. It's a cold, dry desert. Okay, at the tropics, we've got the hot desert, and at the poles, we've got dry desert. So sometimes the questions will ask you about what happens at low pressure, rainfall, and sometimes it will ask you what happens at high pressure, deserts. So hopefully that might cover quite a lot of the other things I've got written down. So that is the global circulation cell and the ITCZ. So the next thing we're going to consider is pressure differences. Okay, so pressure differences. So the only thing with that one that we have to remember really is that air always moves from high pressure to low pressure. Okay, always goes. So they are the trade winds. All right, so when you've got your global circulation map, you've got your air that's risen at the equator. It's gone sideways in the air, up in the atmosphere. It's dropped back down, and now it wants to go back to the equator. And because of the spin of the Earth, if you remember the Coriolis effect, then it doesn't go straight back down, it goes at an angle, doesn't it? Because the Earth is spinning. So they are, that's pressure differences. So air always flows from high pressure because it's being pushed downwards, and then it's flowing outwards, going back into somewhere where it can rise again. So it always goes from high pressure to low pressure. Okay, so I think that covers that quite quickly. Next one I'm going to consider is ocean currents. So, ocean currents, you're often asked 2 or 3 marker, I think, for this one. What's the role of ocean currents? And you have to be very careful that you say that ocean currents, the role is to move heat through the water. It's nothing to do with the air because it's ocean currents, okay? Don't make that mistake. So the role of the ocean current is to move hot water from the poles, from the equator to the poles. So obviously when the sun is heating up the land, it's also heating up the oceans. So the oceans are getting very hot, and then again circulation cells happen within the oceans. Top of the ocean is warmed up, that starts a movement, and it moves hot water from the equator to the poles, and that means that we don't get overheating of the planet, and therefore we can live on the planet. When it gets up north to the poles, it drops back down again because it's cold, comes along the bottom of the Atlantic Ocean or wherever it is, then it rises and heats up again. So that's another kind of circulation cell. So that is our first thing there. Right, let's go on to page 2. My writing is all over the place. Right, rainfall zones, which you can hardly read, but it's there. Rainfall zones. So we've just talked about that, haven't we? We just said that rain falls in areas of low pressure because air is sinking, okay? And when we've got areas where we've got air rising, that's low pressure. And when that air is sinking back down again, that's high pressure. And we've got no rain. Hopefully I've got those the right way around. Now, the next one says high pressure deserts, and I think we've covered that one. So yeah, the deserts can be a hot desert at the tropics or a cold desert. So if you get a question on that and it will say deserts with an S, then you need to talk about the fact that in the Hadley cell, when that air is dropping, it's forming high pressure and no rain. And then when the polar cell, when the air drops at the polar cell, right at the top at the North Pole, that is also causing high pressure and no rain as well. Okay, I've talked about a little bit about West African rainfall. That can come up as well as a question. Why does West Africa get a rainy season? And we just kind of considered that. So because of the tilt of the Earth and the Earth moving around the sun, okay, sometimes that area of Mali, sometimes it talks about, is moved out of, it's northwards in the winter time, it's tilted backwards. So it's out of the low pressure zone and it's in the high pressure zone. So that is Mali's dry season. And then when the Earth spins around the sun and it's at the other side, it's tilted towards the sun and it's going into that low pressure zone. Okay, so it goes into and out of the ITCZ essentially. So it gives Mali seasons: rainy season, dry season, rainy season, dry season. So hopefully that's okay. Right, so we've done that one. Next one, we're on to now greenhouse effect, etc. So let's see, which one should we start with? So I think it's evidence of past climates, and hopefully I'm going in the order of the book, of the GCSE textbook anyway. So evidence of past climates. Now, if we remember, we have got, I'll just find the place in the book for this. So yeah, we've got 4 wrong one. Natural causes of climate change. Natural causes of climate change, that's the first one. So that is our eruption theory, if we remember, where volcanoes erupt, they put sulfur dioxide and ash and dust into the atmosphere. That forms a blanket, and we're not able to get any incoming solar radiation, so it causes cooling. Okay, this causes global cooling. And that can go on for a while, but not too long. So this is kind of shorter term really than some of the other ones, because the other ones are over a longer period of time. The second one is asteroid collision. This is very similar, where we had an asteroid hit the Yucatan Peninsula, maybe made the dinosaurs go extinct, and again hits into the Earth, throws up all this dust cloud and bits and pieces into the atmosphere, stopping again incoming solar radiation. So we have cooling, and again that's over a period of years and decades rather than millions of years, etc. So they're the two things. They're shorter term. So they've got less of an impact, I would say, if you're asked a question about evaluating these theories. The next one is sunspots. So that's over a much longer period of time. And that is where we've got spots on the sun. Now remember, the dark spots are hot. So when the sun has got hot spots on it, it's hotter. So that means that more radiation reaches the Earth and it's hotter, our planet's hotter. And that counts for things like the warming period, the medieval warm period, and the little ice age and things like that, when there were less spots on it, etc. And that kind of thing. So they're much longer periods of time, so we don't notice them as much, being people, obviously, because we, hundreds of years, we don't live for hundreds of years. So that's okay. So that causes heating and cooling, unlike the other two. And then finally, the orbital theory. There's a lot about the orbital theory, isn't there? So mostly the orbital theory means that mostly we are going in a circular orbit around the sun. So we are at equal distance to the sun at any point, but sometimes that changes to an elliptical. So instead of being round, it's elliptical. So sometimes we're further away, it's cooler. Sometimes we're closer to the sun, it's hotter. And then obviously we've got this wobble of the axis. Remember, I just talked before about the axis of the sun is of the planet is like, we're not straight like that going around the sun. We're on an angle, so we're on a tilt, and sometimes that wobbles. Okay, so that puts us either closer or further away, so that can have an impact as well. But again, that's over a much longer period as well. That's really, really quick. It takes like 41,000 years for that axis tilt to move backwards and forwards. So they're big amounts of time, and they're heating and cooling. Okay, so next I am going to talk about evidence of past climate change here. That's our next one, evidence of past climate change. So these are at different scales, really. So in the longer term, we can look at ice cores. So they're in the distant past. And ice cores, if you remember, are scientists drill into the North Pole, where we've got this massive build-up of snow and ice over thousands and thousands and thousands and millions of years, whatever. And they've got carbon dioxide trapped in it. So when the snow falls, it also takes in little pockets of, little molecules of carbon dioxide. So when we've got high levels of carbon dioxide found in the ice core, it means it must have been hot. Okay, so remember that. You can talk about pollen and stuff like that, but it's much easier to get the marks if you talk about carbon dioxide. So carbon dioxide in the ice means that it was warmer, and less carbon dioxide in the ice means it was colder. So that's in the distant past. That's quite reliable. So if we're talking about reliability, that's quite reliable. Next, we are talking about tree rings. So that's kind of medium term, really. So that can be couple of hundred years, because trees are about a couple of hundred years old, aren't they? So tree rings, obviously, each year that the tree grows, the ring shows another year of growth. So when there was a very short growing season and it was quite cold, the tree ring, the gap between the two dark bits is very little. And that shows that it didn't grow very much. If there's a bigger gap, a lighter gap between the dark bits, which is the bark kind of thing, then it shows that there was a long growing season, so it was warmer. So you can see periods of time when there's big gaps between the rings, it was hotter, and when there's small gaps between the ring, it was colder. Historical source, that's quite reliable as well. Historical sources, not so reliable, if you remember. They're things like old photographs and drawings and paintings, written accounts, and we talked about iced frost fires on the Thames in some of the pictures, that oil paintings and stuff by famous artists. We're talking about books that were written. Charles Dickens wrote Christmas Carol, talked about it being really, really cold. But remember, they're not that reliable because they might be like having artistic license to exaggerate, etc. So we have to be a little bit careful with that. And then obviously up to date, we've got satellite images, which are very reliable because that's using technology. Okay, so our next one is greenhouse effect. The greenhouse effect. Now, greenhouse effect, we do this even in lower school, don't we? So the greenhouse effect is when we have got greenhouse gases in the atmosphere. They can be methane, carbon dioxide, nitrous oxide, H2O, remember water. That forms a layer And then the important thing is that incoming solar radiation is short wave. Now, short wave has got a lot of energy, so it's able to get through the layer of carbon dioxide and nitrous oxide. When it hits the planet, it changes wavelength, okay? It changes to long wave. So that's got less energy, okay? Short wave is like little children running about, loads of energy, and then it hits the planet and it loses that energy and it becomes old like me, and it's got less energy, so it's slower, it's got a lot of, it's a bit, you know, it's a bit lethargic, etc. So as it bounces back, it heats up the planet, obviously. So comes in, shortwave, hits the planet, heats it up, the land, up the sea, bounces back. It's not got a lot of energy, it's quite old. So it can't get out. Some of it gets out, some of it doesn't get out, and then it bounces back. So, okay, that is the greenhouse effect. Now, we need greenhouse gases in the atmosphere. Be careful with this. If we had none, then we wouldn't have a planet that was hospitable, because all the heat would escape and we wouldn't be alive. So we have to have greenhouse gases. We've always had volcanic eruptions. We've always had natural forest fires. We've always had methane being released from rotting vegetation and ice caps and the oceans and things like that. Okay, so just remember that. But what we're doing, obviously, is we are, yeah, my next one is enhanced greenhouse effect. I think I finished the greenhouse effect. So yeah, the greenhouse effect, some of it gets out, some of it doesn't, because it's long wave radiation. But the more greenhouse gases we put in the atmosphere, the enhanced greenhouse effect. Now, this is what we do as people. We add more stuff to the atmosphere by burning fossil fuels, eating more cows, so it's more methane produced. Global warming is melting the ice caps, so methane's coming out of those ice caps that's trapped beneath the ground in the tundra regions, etc. So we're adding to it. So that's the enhanced greenhouse effect. So we're making it worse. Okay, let's have a look. I think I've done all of those. Evidence, natural causes. Yep, I've done all of those. So that's that one done. That's pretty quick. Right, our next one, let's have a look. So we said the enhanced greenhouse effect, didn't we? Right, I think the next one is thermal expansion. I don't know why that's got a 15 on it, but never mind. It's because it's on the back. Anyway, so thermal expansion. So that is when this is causing sea levels to rise, okay? So obviously sea levels rise when we have land ice, not sea ice, land ice melting, okay? Glaciers on Greenland, glaciers at the South Pole, not the North Pole, because that's like an ice cube that's already in water, so that makes no difference. If you get a cup of water, put an ice cube in, and then the ice cube melts, doesn't make any difference, okay? So it has to be land ice. Now, so that causes sea levels to rise, but the other way that sea levels rise is through thermal expansion. So as the oceans get hotter, when things get hot, they expand. I'm not a physicist, that's all I know, that's all you need to know. So we have thermal expansion. So the hotter the sea levels get, the molecules expand, okay? If I haven't got the right, then go and ask your physics teacher. So that's thermal expansion, that's here. Right, future scenarios I think we're up to. So future scenarios. So what's going to happen in the future? What do climate scientists think is going to happen? Well, they're not sure. So there's three scenarios, if you remember. There's option A, option B, and option C. So let's start with option C. That's the best case scenario. It's probably not going to happen. That's where we have low population growth in the future. So we slow down. So people aren't, doing as much and buying as many things and going around on aeroplanes and everything. We have renewable energy as the main source of energy, and we have recycling, and sea levels only rise by about 30 centimetres. So that is like best case scenario, but that's probably not going to happen, because as we know from COP26, there's COP27 coming, they just can't make any decisions. Next one is lower population growth, some renewable energy, and a moderate economic growth, especially of the BRICS and things like that. That's possible. Okay, that's the one that we're hoping for, that we only get like 1.5 degrees of warming. But it's very, it's difficult to know what green technology we're going to have. It's very difficult to know what populations are going to do, and it's very difficult to know, how much the BRICS and those emerging countries are going to want to develop without green technology, with the use of fossil fuels. And then option A, this is on page 23 of your textbooks if you're using the Leopard textbook. Option A is the worst case scenario, which we're in at the moment and maybe we won't get out of. That's high population growth, which we've got. We know we've got that in India and China and places like that. Fossil fuel use, which we have got. High economic growth, and sea levels will rise to 1 metre and above. So do we know? No, because it's very difficult, because we don't know what the population's going to do. We don't know what population policies countries are going to have, etc., etc. So it's difficult to know, all right, but we do know that climate change will bring more frequent flooding, more frequent hurricanes. It will bring stronger storms, changes to farming, and farming will have to change and adapt to warmer or drier conditions. And we'll have a lot of climate refugees, basically, of people living in low-lying areas like Bangladesh, which is one of our case studies, because they will not be able to have the money to mitigate. Okay, we can mitigate, we can put things in place to change, or not to change, but put things in place to make sure that we're not impacted, but people in poorer countries can't. Okay, so future scenarios. Right, so we're up to now, quickly getting on, we're up to cyclones, okay, tropical cyclones or hurricanes. So please remember that tropical cyclone, hurricane, and whatever else it's called, it's the same thing. They're called hurricanes, cyclones and typhoons, depends on where in the world. So if you get a case study question on this or a bit of a resource, then just remember it's the same thing. So yeah, tropical cyclones, they're within the tropics. Remember, they can't form at the tropics because of the Coriolis effect, doesn't work at the tropics. Just doesn't happen, water goes down. Don't know if you've seen that nice video on YouTube where they're in Uganda and there's like a yellow bowl and this man is showing this little flower. Don't know if you've seen it. I might try and put a link if I can do that. It's a nice little video. So if we're to the north or the south of the equator, then we get that spin of the earth. So they form either side. Okay, they spin out from the equator. And they only form within the tropics, really, because you have to have sea surface temperatures of about 27 degrees. So they happen there. They are measured on the Saffir-Simpson scale. That's a wind speed scale, okay? And they go from 1 to 5, depending on how high they are. Once they get over 74 miles an hour, they can be classified as a hurricane, and they can get up to like over 157 miles per hour, and that would be like a scale 5 of that one. Right, okay, so hazards, they bring strong winds. Of course they do. They bring storm surges, which, remember, means when the tide comes in, you've got a very, very, very strong wind. It will push the water, obviously it will push the waves onto the land. So that's a storm surge. So when you've got high tide combined with a very strong wind, you've got a problem. Okay, coastal flooding, therefore, intense rainfall, of course it does, and landslides are a big one as well, because you've, especially in poorer countries, because you would tend to have people, especially poorer people, will tend to build their houses in areas where no one else wants to. So unfortunately, they're the ones that are being affected. So you've got a lot of landslides and a lot of houses, you know, destroyed, unfortunately, in those poorer countries. Okay, so let's have a look. The formation of hurricanes. You can hardly read it, but there it is. It says formation of hurricanes. So like I said before, you've got to have warm water. You've got to have the Coriolis effect. Generally, they form over, if you're talking about American ones anyway, they form over West Africa, and they're generally some individual storms, which, because of the Coriolis effect, kind of merge and come together. So just one storm by itself won't be big enough, but often as 2 or 3 storms form there, they're pushed across the Atlantic, and they merge because of the Coriolis effect into a bigger storm, and they build up from there. There has to be low wind shear in the upper atmosphere, otherwise the storm gets ripped apart. There has to be sea surface temperatures 27 degrees, and it has to be over the oceans, obviously. Okay, once it hits land, it will dissipate. Obviously, you've got those swirling winds and clouds because of the Coriolis effect, and it's very, 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 very low pressure. And the lower the pressure, the stronger the winds, basically. So you have like over 1,000 millibars as the average air pressure over the seas, but it drops quite low when it's much low pressure in a hurricane, because everything's rising, obviously. I think that's about all for that one. I'm not going to go over that too much. Right, so impacts, formation of hurricanes, tropical cyclones. I think I'm on my last one now. Maybe, maybe not. Impacts, yeah, there we go. Impacts in low-income countries and high-income countries. So, right, impacts. Obviously, there's greater impacts in low-income countries. Okay, now Bangladesh will be your example here. Now, be careful. Not be careful, but think about Bangladesh. Okay, the reason why it's at risk is that, one, it's a poor country, but from a physical geography point of view, physically, it's very low lying. Okay, most of Bangladesh, most of the southern areas of Bangladesh is only about 2 meters above sea level. That's ridiculous. So it's very low level. So even in a very high tide, a very high spring tide with a storm, most of Bangladesh would kind of get flooded. So 2 meters above sea level. It's on a delta. So Bangladesh is basically a river. Okay, it's a river flowing out to sea. And, you know, unfortunately, you know, quite poor, you know, quite low income people in the world have been forced to live there. because they've got no alternatives. So very low lying area, it's right on the coast. Okay, obviously it's coastal, it's very low lying, and it's on a delta anyway, so it's got a river coming through it. So when we get storm surges and when we get storms, two things happen. The storms push into the land, and the rivers, because of the heavy rainfall, the rivers also overflow. So you've got like a double issue of flood risk. Does that make sense? So you've got the land with the river on, so the river's getting overflown because there's too much water, and then the sea with the storm surge is pushing in and pushing the water onto the land as well. And then obviously it's very low lying. Most people there are farmers, etc., because it's quite rich. The delta area's got quite nutritious and rich soils, so huge amounts of people affected there. So Cyclone Ayla, which is in May 2009, which is the case study in the book, 190 people died, 750,000 made homeless, etc. They were displaced, lowest income groups worst affected on the delta land, etc. Crops were ruined because of salination of incursion of salt water. 3.5 million people were affected, losing their homes, etc. Lots of cattle and land, so environmental issues, economic issues, social issues, okay, impacts. So huge amounts of devastation there, all right? Now, if you're talking about the HICs, which is the USA, I'll just flip onto that quickly. Now, obviously, it's less impact because it's a high-income country. So overall, if you get an evaluation question or an assess question, assess the impacts in different countries, then obviously you're going to say that there's less impact in a HIC. However, there is a little nuance there because the storm, I want to say Storm Matthew. I want to say that. Should have written that down, really, shouldn't I? Anyway, the storm that happened it was Katrina. It was Hurricane Katrina. I'm an idiot. So in 2005, Hurricane Katrina hit the USA, hit the coastline, and caused huge amounts of damage. Now, parts of New Orleans generally, it's not a massively rich city, I should say, and the levees broke. Okay, so there was levees, the river running through the Mississippi, one of the biggest rivers in America. The levees broke because there's just so much water. Again, the same thing, rainwater in the rivers and then the storm surge. And the levees broke, and so you had a situation where it caused huge amounts of damage. All right, so if we're evaluating that, what we can say is that overall, the impacts are less. But in this particular instance, there was a huge impact of that. And afterwards, Obama got criticised quite heavily because he didn't send the National Guard and stuff in, and there were calls for, because there was high ethnicity in the city, and a lot of people said if this had happened in Florida, where there was the majority were white, rich, middle class people, then the army would have been there helping out and everything. So there was a lot of political issues related to that. But as it was, huge areas were flooded, loads of people lost their homes, quite a lot of people lost their lives, etc. in those areas near the river. So that would be your assessment that actually, there are times within high-income countries where, they don't get it right. Okay, so let's have a look. We need to go back a little bit. So we've got impacts and analyses, risk assessment and evaluation. Let's have a little look here. We're nearly at the end. We're running at about 27 minutes, but I'll keep going. So let's have a look. We've got management. Okay, management in HICs and LICs. So obviously in America, it's a lot better managed, apart from what happens in New Orleans. But generally, you've got warning systems, you've got preparation, you've got planning, you've got places for people to go, you've got resources there, clean water and food and shelter and that kind of thing. So better management. Although, like I said before, do make sure that you write that, because you'll get extra marks for that if you talk about Hurricane Katrina. Now, it wasn't managed very well. If we're talking about low-income countries, then when we're talking about Bangladesh, we are talking about the fact that there are warning systems, although they use Chinese or Indian satellites. There are more warnings in the urban areas than the rural areas, so that's a bit of an assessment. And also we have to think about literacy within rural areas is lower, so sometimes people either can't read the leaflets. Also, electricity supply means maybe there's not enough radios or TVs to get that warning out. There's not as much management, obviously, because it's a poorer country, but there are shelters. Remember, there are shelters being built along the coastline, and they work quite well, and people were evacuated to them, but some people didn't want to leave because they didn't want to leave all their stuff and get it ruined, and it was not there when they got back. And like I said before, more people were helped in the cities than the countryside. Overall, it's not as bad as you might think, so don't go down the line of like it was terrible and nothing happened. It did. There are management issues there, and it did It has improved because the country is spending money, the government is spending money on warning systems and evacuation and things like that. So it's not all bad, and make sure you know a few facts and figures for that. Running into the next one, which is risk assessment and evacuation. Risk assessment and evacuation. Now, risk assessment, I'm going to show you a little picture here. Okay, it looks like this. This come up a couple of times, something like this. So as you can see, this is colour coded. This is in America. Okay, and this is colour coded. This is Florida, and it's colour coded dependent on which areas are at risk. So do be aware of you assess the risk, especially in rich countries. Which areas would be more at risk? The low-lying areas, obviously. Which areas are less at risk? The areas either with defences or the areas that are higher up. So this map is colour-coded with low, moderate, high and extreme, etc. Potential storm surge. So the areas obviously right on the coast, if they haven't got defences, will be very high risk. As you go inland, it'll be low risk. So just bear that in mind, okay, that even in a rich country, hurricanes hit. All right, so the area right next to the coastline of this low line, that's going to be worst hit. So that's going to have a high risk. So you're going to have more evacuation plans there. You're going to have people ready to evacuate, etc. If you're further inland and you're higher up and you've got more defences, etc., then you're going to be at lower risk. So just be aware of that. So that is risk. And then you evacuate people, obviously. So that's risk zones, okay? And then I think I've talked about this, forecasting, warning and satellite technology, which I should have done before, but I didn't. So forecasting comes from satellite, so you can track the hurricane to see where it's going to go. If you know it, possibly you're not always going to get it right, but you can forecast maybe where it's going to be and then evacuate those people. You can give people warnings. It's going to work very well in richer countries because everyone's got access to TV and radio and mobile phones and everything. It's going to work less well, especially in rural areas in LICs. So be aware of that, where people have got less access maybe to technology, etc. And that satellite technology, obviously America's got its own satellites, but other poorer countries maybe don't, and they rely on information come from other countries which can have delays. Okay, so I think that's all. So that is the first section of Hazardous Earth, and that's all to do with climate change and hurricanes. I'm going to hopefully make another couple of these videos. I'll make one on Hazardous Earth, and then we'll get on to development dynamics. So have a good evening.